So in chapter 20, we are going to talk about enols and enolates. We are going to talk about enolates of aldehydes, ketones, esters, diketones, diesters, and so forth. We're going to start with the terminology. If I am looking at an aldehyde, the carbon that is attached to an alpha carbon is referred to as an alpha carbon. The adjacent carbon will be a beta, and then the third carbon will be a gamma. The hydrogens that are attached to alpha carbon are alpha hydrogens. The hydrogens that are attached to the beta, there will be beta hydrogen, and the hydrogen that are attached to the gamma, there will be gamma hydrogen. In enol and enolates, we are talking about the acidity of the alpha hydrogen, or alpha hydrogens if we have more than one. So the acidity, it starts with having an appropriate base, and we're going to discuss that in details. So I have some kind of an R group, and I have CH2, C double bond O, H. If I have a base, then I can take the beta hydrogen and form the enolate. This is the structure of the enolate, or CH double bond C O minus hydrogen. Now, what I did on the board, I drew the most stable, or the more, because we only have two resonance structures here, the more stable resonance structure of the enolate. So I drew the more stable resonance structure of the enolate. This is a less stable resonance structure. This hydrogen is relatively acidic. The pKa value of an alpha hydrogen in an aldehyde is in the order of 16. It is less acidic in ketone, and we'll refer to that later. So for instance, if you are looking at this aldehyde, the pKa value of this alpha hydrogen is 15.5, while in acetophenone, the pKa values of these hydrogens are 18.3. Do we have any alpha hydrogens here? No. So we only have alpha hydrogens at the metal, the same right here. This hydrogen is not acidic. Now, if you have an aldehyde and you add a hydroxide ion, sodium hydroxide, you will be able to generate the enolate. More importantly, what you are going to have in the reaction mixture is 50% of the enolate, 50% of the aldehyde. In other words, you will be able to have a nucleophilic attack. The enolate is going to attack the aldehyde, and that we will refer to as the aldol condensation. So at this stage, what I would like to draw your attention to is the following. If you take an aldehyde and you add a hydroxide ion, you're forming an enolate, and you are actually getting the equilibrium constant here is closer to 1. So you have an equal molar ratio between the enolate and the aldehyde. Now, if you would like to generate the enolate quantitatively, which means you want to have 100% enolate, you want the K to be much larger than 1, you need to use a much stronger base. This equilibrium constant here is closer to 1 because the pKa value of water is close to the pKa value of the starting aldehyde. That's why you are having equal molar ratio between the enolate and the aldehyde. What about the acidity of the alpha hydrogens in beta diketone? This is a beta diketone. We call it a beta diketone because at the beta carbon I have another keto group. So this is a beta diketone. Now these hydrogens are more acidic. The pKa values of these hydrogens is in the order of 9. This has to do with the fact that the enolate that you will form upon deprotonation of this alpha hydrogen is more stable, and it is stabilized by resonance. So if I want to use a base to form the enolate in a beta ketone, you have a base. So the base is going to pick up the alpha hydrogen, and you will form the enol. Your enolate, and I am forming the more stable enolate, is more stable. It is more stable because of resonance. You will be able to generate two equivalent resonance structures, which are shown on the slide. Now, what about the acidity of an ester? Well, the alpha hydrogen in an ester is less acidic. This has to do with the fact that if you take this, if you look at the resonance structure of this carbonyl, you have a plus and O minus here, and this plus charge is stabilized by having an oxygen which can get an adjacent oxygen which can give electrons by resonance. In other words, you have less plus charge at this carbon. This will lead to having these hydrogens to be less acidic. In fact, in simple esters, the pKa value is in the order of 24 of alpha hydrogens. You cannot generate enolate unless you use a very strong base. For instance, using an amide ion or lithium diisopropyl amide. That will be an even better choice, an LDA. So in esters, for instance, ethyl acetate, you cannot completely deprotonate them by just adding an alkoxide ion, and we're going to talk about that in details when we talk about what's called Claisen condensation. That will be covered probably next lecture. Ethyl acetoacetate and diethyl malonate, they are also going to be covered in the next lecture. They can be completely deprotonated by alkoxide bases. You will see that the alpha hydrogens are more acidic, again, because the conjugate base is stabilized by resonance. While if you want to talk about simple esters, you can use LDA. LDA is strong enough to deprotonate the alpha hydrogen in an ester, and you will be able to get the enolate of the ester quantitatively. Also, LDA is bulky. It is too big. So you will not have nucleophilic addition between LDA and the carbonyl. You will only have an acid-base reaction. So this is LDA. If you use LDA, you can form the enolate of an ester quantitatively. So let's say I have ethyl acetate, and you are adding LDA. Now you do not have an equilibrium anymore. What you are going to have a quantitative formation of the enolate. So the LDA this N minus is going to pick up the alpha hydrogen, and you will form the enolate quantitatively, 100%. So where you are going to form a CH2 double bond C, O minus O, CH2, CH3. So you can form an enolate out of an ester by using a stronger base, which is the LDA. So if you take, for instance, the methyl butanoate and you use LD8, you can generate the enolate of the methyl butanoate quantitatively. The pKa of the conjugate acid of LDA is 36, while this pKa value is 22. So you're going from a stronger to a much weaker acid. So this is a first slide comparing pKa values of the different keto compounds. Well, here I have a ketone, here I have an ester, here I have what's called a beta ketoester. I have an ester here, and at the beta carbon I have a keto. The pKa value of this alpha hydrogen is 16 to 20. The pKa value of this hydrogen in an ester is in the order of 24. The pKa value of this hydrogen, the alpha hydrogens here, is 11. So as you can see, I have these hydrogens here to be the most acidic among these three different compounds. Fine. If I have an aldehyde and I add a hydroxide ion, I will be able to form an enolate. The K is in the order of 1. This has to do with the fact that the pKa value of this aldehyde, for instance, is like 15.5, that of water 15.7, so they are equal, almost equal. So you have almost 50% enolate, 50% aldehyde. While if you are having a ketone and you want to deprotonate, you want to form the enolate, you need to use much stronger base. You use an LDA, and then you can generate the enolate quantitatively. The K, the equilibrium constant here, is 10 power 18. And as I also said earlier, LDA is sterically hindered that you do not have nucleophilic attack between the N- and the carbon. So you do not have this nucleophilic attack. Then, if you take this enolate and when you are forming this enolate and you have the aldehyde in the medium, you are going to get a nucleophilic attack between the enolate and the aldehyde. And that will get you a condensation product that we will call aldol. Now, before we go there, what if you have two different types of alpha hydrogens? For instance, if you look at 2-methyl cyclohexanone, well, you have two different hydrogens, two different alpha hydrogens that are acidic. One of them will form an enolate that is more stable, and we will call that enolate the thermodynamic enolate. And there is another enolate that will be formed faster, and we will call it the kinetic enolate. So if I have the 2-methyl cyclohexanone, well, I have two alpha hydrogens, two different alpha hydrogens. This is one, and I have these two hydrogens to be equivalent. Now, if I have a base that is taking this beta hydrogen, this alpha hydrogen, I'm sorry, it's taking this alpha hydrogen, you will be forming this enolate. O minus double bond CH3. However, if you, let me draw it again. Now, if you have the base to pick up this alpha hydrogen, you are going to form this enolate. Now, this enolate is called the thermodynamic enolate. It is the more stable enolate because the double bond is substituted with a methyl group. Now, this enolate is called the kinetic enolate. It is formed faster because this hydrogen is not as sterically hindered as this hydrogen. So the base can reach these alpha hydrogens faster than this hydrogen. That's why we call it the kinetic enolate. It is formed faster. Now, whether you get the thermodynamic enolate or the kinetic enolate, it depends on the structure of the base, for instance. Let's say you are using LDA. What do you think is going to be the enolate that we will form if we get LDA, if we use LDA?
LDA, as we said, is a bulky compound, so it would be more hindered to attack the methyl substituted carbon. So we will get the kinetic enolate.
Absolutely correct. So if you use LDA, you're going to form the kinetic enolate. Because LDA is sterically hindered, it's big, you cannot go for the thermodynamic. So the choice of base can favor the kinetic over the thermodynamic. The solvent, the temperature, what do you think is going to be the enolate that you will form if you have higher temperature rather than lower temperature? The thermodynamic. The more stable enolate is going to be formed at a higher temperature. So we're going to go over some examples which would favor a kinetic over thermodynamic or thermodynamic over kinetic. Now we will go into our first condensation, which is the aldol condensation. We agreed that if you have an aldehyde and you add sodium hydroxide, you are going to get 50-50 mixture between the enolate and the aldehyde. So let's say I have, we will use first a generic formula of the aldehyde, and then we'll go over some examples. So let's say I have R CH2 C double bond O H. And I am adding a hydroxide ion. This hydroxide ion is going to take the alpha hydrogen, and you are going to form the enolate. R CH double bond C O minus H. Then, in the reaction mixture, as we just agreed, we have a 50-50 mixture between the enolate and the aldehyde. What will happen next is that this enolate is going to attack the aldehyde. Where is it going to attack? It's going to attack the carbon. So what you are going to have next is R CH2 C. I'm going to draw it this way. What you are going to have is that the enolate is going to attack the aldehyde. And what you will form, R CH C double bond O H C O minus H CH2 R. And then this will pick up a hydrogen from water, and what you will form is CH C double bond O H R CH OH CH2 R. So H C double bond O CHR CHOH CH2 R. Now this is called the aldol product. Why do we call it aldol? Because you have the aldehydic group here and you have the alcohol group here. Now, if you heat this up, and sometimes you don't even need to heat it up, even at room temperature, elimination will occur. Elimination will happen, and you will eliminate the beta hydrogen to the hydroxyl. Now, the beta hydrogen, I'm using the beta hydrogen for the elimination terminology. So now our alpha carbon is the carbon that is attached to OH. How many different beta hydrogens to the OH do you have? Two. Which one do you think are you going to eliminate? You are going to eliminate this hydrogen so that the C double bond C is in conjugation with the C double bond O. So the final product is going to be RCH2 CH double bond C R C double bond O H. This is going to be your product. Many times, you are going to get the elimination product of the aldol even at room temperature. The driving force for this is the conjugation between the double bond C double bond C and C double bond O, which is a more stable compound. So we're going to go over many examples right now. So what I'm going to do, I will just put, for instance, propanol, and I will add hydroxide, or a butanol, and then basically you have different R groups, and you will get different aldol products. Let me go over examples, and then I will open the floor to any questions you might have. So the basic solution, to recapitulate, the basic solution will have comparable amounts of the aldehydes and its enolate. The aldehydes will undergo nucleophilic additions, where the enolates are going to be our nucleophiles. So the first step is the formation of enolate. I'm forming the more stable enolate. And then the enolate is going to attack my aldehyde, and I will get the conjugate base of my aldol product. And then the conjugate base is going to pick up a proton from water, and that will get me my aldol product. It's called aldol because I have the aldehydic group and I have the hydroxyl group. So let's say I have acetaldehyde. So I'm going to erase it, though it is exactly the same mechanism. I'm going to erase it, and then I'm going to do it again. So what is the aldol product of acetaldehyde? Well, CH2, H, C double bond O, H. I'm adding a hydroxide ion. This hydroxide ion is going to take the alpha hydrogen, and you are going to form the enolate. CH2, double bond C, O minus H. And then the enolate is going to attack another mole of acetaldehyde. You have equal amount between the enolate and the aldehyde. So this is CH3, C, double bond O, H. And what you're going to form is C, double bond O, H, CH2, C, O minus, CH, CH3. And then in the presence of water, I am going to get CH3, CH, OH, CH2, C, double bond O, H. Heat it up. You will form the elimination product. CH, double bond, CH, C, double bond O, H. So that will be the elimination product of the acetaldol. Another example. So this is at 5 degrees at low temperature. Another example, you have butanol. And then you are adding KOH-H2O also at low temperature. So we are forming the aldol. That will be the aldol product. So this is our aldol product. If you heat up the aldol product, you will get the elimination. So if you take this and you add just sodium hydroxide and heat, that will be the product that you are going to form. So if you take butanol and you add sodium hydroxide and water at 80 to 100 degrees, you are going to form the 2-ethyl 2-hexenal. Because you are going to have elimination, you will always eliminate so that you have the C double bond C to be in conjugation with the C double bond O. Fine. And you can do this elimination under acidic conditions or under basic conditions. Now, what about ketones? The problem with ketones is that if you just add sodium hydroxide, you have in this equilibrium 2% leading to the aldol product, while 98% are still at the keto, which means you only have very small quantities of the aldol product. That's why sodium hydroxide will not be a good choice to form the enolate of a ketone. If you use LDA, however, you can generate the enolate of the ketone quantitatively, and then you can drop any other aldehyde or ketone, and you will get what's called a mixed aldol condensation, which I will talk about in a minute as well. So having a ketone and adding sodium hydroxide cannot lead to the formation of the aldol product of that ketone. However, if you take this diketone and you are adding sodium carbonate and water and you're heating up, you are gonna get an aldol condensation product. It is an intramolecular condensation, and you are forming a 5-member ring. This is favored, such intramolecular aldol condensation, when you are having a 5-member ring or a 6-member ring. In fact, if you have the choice to form a 6-member ring versus 4-member ring, you should go for the 6-member ring. So this is an example. Let me actually make another example. Does it ring any bell? Okay. So I have this diketone, and I am adding a base. Okay, sodium hydroxide. Now, how many different alpha hydrogens, I'm referring to the acidic hydrogens here, do I have? Well, what first, you know what? Where are our acidic hydrogens? Let's identify them first. I have acidic hydrogens right here. I have acidic hydrogens right here. And I have acidic hydrogens here and here. But these two are the same as these two. Now, if I form enolate here, the enolate is going to attack this ketone. If I form the enolate here, it's going to attack this ketone. Now, I have two choices. Either I will form this enolate and I will attack this ketone, or I will form this enolate and I attack this ketone. So let me call them A and B. So let's say I have the acidic hydrogens here to be labeled A, and these acidic hydrogens to be labeled B. Which one do you think is going to be deprotonated? Well, right here I have 1, 2, 3, 4, 5, and on this side I have 1, 2, 3, 4, 5, 6. So I have 1, 2, 3, 4, 5, and then I have 1, 2, 3, 4, 5, 6, 7 actually. 5 and 7. Okay? Right here I have 1, 2, 3, 4, 5, and it is also 1, 2, 3, 4, 5, 6, 7. So that's not a good example. What about now? So now this is A, B, this is C, this is D. So I have these hydrogens, A, B, C, D, all of them are acidic. Which hydrogens do you think are going to be deprotonated? And subsequently, where am I going to have the nucleophilic attack? If A attacks this carbonyl, what kind of ring do I get? 1, 2, 3, 4, 5, 6. And right here I will have 1, 2, 3, 4, 5, 6. 2 6-member ring. Right? What about here? Then I will have 1, 2, 3, 4. And the second one is going to be 1, 2, 3, 4, 5, 6, 7, 8. So A attacking the carbonyl. What about here? C, if it attacks this carbonyl, I will get 1, 2, 3, 4. It's the same as before. So basically, I have these two the same as these two. But now I have choice. Do I attack to form a 4-member ring, or do I attack to form a 6-member ring? You need to form the 6-member ring. So what is the mechanism of the reaction? We agreed that the hydrogens that we are going to deprotonate are these hydrogens. So this is my hydroxide ion. This hydroxide ion is taking this alpha hydrogen. I am forming this enolate. So we're still talking about equilibrium for now. And then, in the next step, I am having the double bond formation. This is attacking. And I am getting O minus. Please number the carbons. If you have any substituents, so that you know where are your substituents. The numbering here is just to guide us to know which carbons are attached to which carbon. So if this is carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I am forming a bond between which carbons? 2 and 7. And the size of the ring is 1, 2, 3, 4, 5, 6-member ring. So what you are forming right now is a 6-member ring. You are having 2 attached to 7, 2 is attached to 3, 3 attached to 4, 4 attached to 5, 5 attached to 6. Then 7 is attached to 8. 8 is attached to 9. 9 is attached to 10. 10 is attached to 1. And 1 is attached to 2. Now I have a double bond over here. And what do I have at 7? O minus. Now this O minus is going to be protonated. And I am getting my aldol product. Now, where are the hydrogens that are beta to the hydroxyl? I have these hydrogens that are beta, but I have one here that is beta. Which one am I going to eliminate? This one. With heat. Why? Because I will get a double bond that is tetrasubstituted, and it is in conjugation with the carbonyl. So my product is going to be this one. Similarly, if I have this diketone, the one on the slide, and I am adding a base, I am going to get an intramolecular aldol condensation where, look here, if I am taking this carbon to attack this carbon, I will get 1, 2, 3, 4, 5, and I will get 1, 2, 3, 4, 5, 6, 7 member rings. So 5 and 7. If I take this carbon, I will get 1, 2, 3, 4, 5, 6, 7, and the second one is going to be 1, 2, 3, 4, 5. So it doesn't matter which enolate is attacking which carbonyl. But in the example that we just drew on the board, it matters. You need to know which hydrogens are you going to have involved in an acid-base reaction to form the enolate, and subsequently what kind of ring you are forming. Do you have any question? Yes, sir.
Is the hydroxide ion strong enough?
Very good. The hydroxide ion right here can take the alpha hydrogen in a ketone because you are forming or you are getting an intramolecular aldol condensation. So the hydroxide ion cannot do the work. It cannot deprotonate. It cannot form an enolate of a ketone unless you are having an intramolecular aldol condensation. Any other questions?
So if you preference the conjugation or substitution?
True. You will always go for the conjugation. The C double bond C to be in conjugation with the carbonyl. But if you have the choice between a C double bond C in conjugation with the carbonyl and a C double bond C that is in conjugation with the carbonyl but it is more substituted, you will go for the more substituted that is in conjugation. But conjugation is always the driving force. Okay? So that is our intermediate aldol, and then upon elimination you will get the product. Now what about having a mixed aldol condensation? Well, first, let's say I am dumping in my reaction mixture 2 aldehydes, and I'm adding a hydroxide ion. Then I'll be in trouble. Why? Because I can form 2 enolates, and each enolate can attack either the molecule from which you form the enolate or the second molecule, so you will get 4 products. So if you are having 2 aldehydes with sodium hydroxide, well, you are going to form 2 enolates. This enolate can attack this aldehyde and you will get this aldol product, or this enolate can attack this aldehyde and you will get this aldol product, or this enolate can attack this aldehyde and you will get the third, or this enolate can attack this aldehyde and you will get the fourth. So basically you are getting 4 aldol products. Fine. What if you want to do a mixed aldol condensation, but you want to decrease the number of products? Well, you can do 2 things. You can use 1 aldehyde that does not have any alpha hydrogens. If you do not have any alpha hydrogens, you cannot form an enolate. You can also use an aldehyde that is reactive to nucleophilic addition more than the other aldehyde. Or you can use both. You have an aldehyde that does not have alpha hydrogens, and it is more reactive towards nucleophilic addition, and then you will be able to decrease this number from 4 to 1. Let's go over some strategies. So in order to effectively carry out a mixed aldol condensation, you can minimize the reaction possibilities by having only one of the reactants to form an enolate, and to use one of the reactants to be more reactive towards nucleophilic addition. For instance, formaldehyde. It's a perfect example. Formaldehyde does not have any alpha hydrogen. Formaldehyde is the most reactive towards nucleophilic addition because you have H and H. You do not have any steric hindrance for a nucleophile to reach the carbonyl. Okay? So for instance, if you take this aldehyde and formaldehyde and you are adding potassium carbonate and water ether. When you have potassium carbonate in water, it means you have a hydroxide ion. Well, You cannot form enolate of this. You can only form enolate of this aldehyde. But then when you are having the enolate of this aldehyde, in the presence of two aldehydes, one is much more reactive towards nucleophilic addition than the second. The product is going to be a mixed aldol condensation where the enolate of this aldehyde is attacking formaldehyde. So the strategy that we used here is to use formaldehyde, which does not have an alpha hydrogen, cannot form an enolate. Formaldehyde is much more reactive towards nucleophilic addition. So once you form that enolate of the second aldehyde, it's going to attack formaldehyde. It's not going to attack the aldehyde itself. And there is your mixed aldol product. Of course, you will still have side product where the enolate of this aldehyde is going to attack the aldehyde itself. But the major product is going to be the enolate of this aldehyde attacking formaldehyde. Second, remember what we said about ketones? If you are adding a hydroxide ion, you cannot have an aldol condensation between the enolate of the ketone and the ketone itself. The percentage in the example that I went over, it was like 2%. You are having the aldol product and you have 98% of the ketone. So you are forming the enolate in a very small quantity. Now, you can have a mixed aldol condensation between a ketone and an aldehyde that does not have any alpha hydrogen. So if you are adding this aldehyde and this ketone, you cannot have any enolate right here. There are no alpha hydrogens. Acetone can form enolate in small quantities, but this enolate will attack this aldehyde. And now you are having a mixed aldol condensation between the enolate of the acetone and the aldehyde. Even at room temperature, even at 30 degrees, which is close to room temperature, you will definitely get elimination in this example. Why? Why do you think extended conjugation here? You have the double bond to be in conjugation not only with the carbonyl but also with the benzene ring. So you have such extended conjugation that such elimination will occur even at low temperature or at room temperature. Aromatic aldehydes, they cannot form enolates. This is an example of what's called the Claisen-Schmidt condensation of a ketone with an aromatic aldehyde. Okay, another very interesting approach to form a mixed aldol condensation is to take a ketone, form the enolate quantitatively. You can do so by adding an aldehyde, and then you just drop an aldehyde on it. So what we are having here you're having a ketone, R1, C, H2, C, double bond O, R2, and you are adding first LDA, second, you're adding an aldehyde, third, you're adding H plus and heat. Upon condition number 1, you are forming the enolate quantitatively. So you do not have any equilibrium. You're having the LDA, this LDA is going to lead to the formation of this enolate quantitatively. That is your product upon condition number 1. Then, when you are adding an aldehyde, we called it R3, C double bond OH. The enolate is going to attack the aldehyde, and you are forming C double bond O, R2, CH, R1, C, O minus, CH, O minus R3. Then, in the third condition, you are adding H plus and heat. So you are protonating and you are eliminating, and your product is CH double bond C, R1, C, double bond O, R2. You're protonating and you're eliminating, and you will get the C double bond C in conjugation with the carbonate. So the approach that we did now, we use the ketone, we formed the enolate of that ketone quantitatively, and then we dropped an aldehyde. When I say I dropped, that's how we are going to do it in the lab. If we want to do this mixed aldol condensation, you will form the enolate first, and then you will add the aldehyde. Why are you going to do that? Because if you are going to put the aldehyde with the aldehyde and the ketone, now you're going to form two enolates between the ketone and the aldehyde. But once you form the enolate of our ketone, you can drop the aldehyde. There will be a nucleophilic addition between the enolate and the aldehyde. And then you can just acidify it. You can control the pH, and you can heat it up, and there will be conjugation, which will lead to an elimination. So elimination because of conjugation. So if you are having this ketone, you do not have any alpha hydrogens here. So this R2, this is another very important point and condition. You want to make sure that the second R does not have any alpha hydrogen. Otherwise, you are going to get two enolates. You don't want that. So you can use a benzene ring, for instance, or you can use a tertiary butyl, as in the example on the slide. So that will get you this enolate. You will drop an aldehyde, and then you add H3O plus. That will get you the aldol. If you heat it up, that will get you the elimination. So I'm going to stop right here, and we'll carry on next time. Thank you.